In this video we're going to go over cosmic rays, so let's get started. So what are cosmic rays first of all? Well, it says that cosmic rays are energetic subatomic particles which arrive in the Earth's atmosphere from outer space. The vast majority of the particles are protons, which make up 89% of cosmic rays. Of the remainder, 9% are alpha particles, 1% carbon, oxygen and nitrogen nuclei, and the rest electrons and gamma rays. So if we summarize this in a table, it looks something like this. So you've got the types of particles here and then the percentage of all cosmic rays. So the protons make up 89%, you've got alpha particles contributing 9%, carbon, oxygen and nitrogen nuclei making up about 1%, electrons contributing less than 1%, and then gamma rays with less than 0.1%. It then goes on to say that when cosmic rays hit the top of the Earth's atmosphere, they produce showers of secondary particles, including electrons, photons, neutrinos, and muons. These particles are called a cosmic air shower. So here you can see that if a proton from space collides with molecules in the Earth's atmosphere, it's split up into a shower of different types of particles. So we've got some pions, some muons, some gamma rays, and some electrons and positrons, and so on. Just to show you a quick simulation to help you visualize this. So if you focus on this part on the right here, we can see that we've got the top of the stratosphere up here, and if I click play, you see that we get a cosmic ray, for example, a proton coming into the top of the Earth's atmosphere. We know that this proton will split up into a shower of secondary particles like this, so it collides with an air particle. For example, a nitrogen nucleus becomes a neutron and creates pions, and these are secondary particles. And these secondary particles can decay further, so for example here we've got some pions decaying into gamma, muons and neutrinos. And these particles can decay even further to get down to the height of roughly the cruising altitude of aeroplanes. So you can see that gamma rays will decay into electrons and positrons at this height. And these particles will make their way towards the ground, and remember this is the particles decreasing in energy as they move down towards the ground. And going back to the notes now, we can see that on the topic of energy, we say that cosmic rays have a wide range of energies. And low energy cosmic rays are thought to come from the Sun, intermediate energy cosmic rays come from elsewhere in the Milky Way, but the highest energy cosmic rays are thought to come from galactic centres, but their origin is still uncertain. So that just means the cores of galaxies, the centres of galaxies. We say the highest energies produced by particle accelerators on Earth are of the order of 10 to the 12 electron volts, which is 1.6 times 10 to the minus 7 joules. But in contrast, cosmic rays have energies in the range of 10 to the 9 to 10 to the 20 electron volts. And we say that the highest cosmic ray particles have energies of about 50 joules, about the same energy as a tennis ball served by Andy Murray at 100 miles per hour. So hopefully you realise that the highest energy cosmic rays can be much more energetic than the energies produced by particle accelerators, and these are already very high energies. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.
Hi, welcome to the lifetime of the tau lepton. So this is the first in a two-part series on measuring the lifetime of the tau lepton. In this video, we're going to give basically two things. First, the motivation for measuring the tau lifetime, and second, an overview of the experimental method used for measuring the tau lifetime. In the second video, which is entitled How the Measured Lifetime of the Tau Lepton Changed Over 30 Years, we'll look at the following. First, the evolution of the measured value of the tau lifetime since the early 80s, which is due to the improvements in experimental precision. Second, how these experimental results can help us understand measurement errors. And third, a demonstration of how scientific understanding evolves over time. Now, most of the physics is going to be in this first video. But even if you're not so interested in the details of the numerical results over time, we would strongly recommend that you also watch the second video. So the stuff on error bars in the second video is useful for understanding measurements in general, not just this measurement of the tau lifetime. Okay. So before we go too much further, let's talk about what that picture is in the first slide of the video. So this picture is of a candidate tau plus tau minus production event from the archived data from the Aleph experiment. Let's see if we can understand what's going on in this picture. The Aleph detector was a cylindrical detector, and what we're seeing here is a cross-section of the detector. The various concentric structures are different parts of the particle detector. In the detector, an electron and positron collide, and they annihilate in the center of the detector, and they produce a tau plus tau minus pair. In the case of this event, one of the candidate taus has gone off to the left, and one has gone off to the right. The taus each travel a short distance that is way too short to see in this picture, and then they decay into other particles. Some of those other particles leave tracks in the detector. The tau that went to the left in this picture decayed into one particle which left a track, and this is the red line on the left half of the diagram. The tau that went to the right decayed into three particles which left tracks in the detector. These can be seen as blue, green, and red tracks in the right side of the diagram. If you'd like some more background information, you can check out the video Discovery of the Tau Lepton, available on this channel. So in that video, we talk about the discovery of the tau lepton at SLAC by the Mark I collaboration in the 1970s, and that discovery earned the Nobel Prize for Physics in 1995.